Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're talking about energy here, energy in a nuclear reaction. This is the last concept we're going to do in nuclear. There are other things we can talk about, but we're getting closer in the year's wrapping up, so I want to just keep it sweet and simple. This does take a little bit of work, so in order to do this, we're going to go back to Einstein's famous equation. E equals mc squared, theory of relativity, where E is the energy in joules, M is mass in kilograms, and C is the speed of light C is a constant speed of light, 3 times 10 to the 8th. Now, the actual number is 2.98, but just to keep it simple, let's make it 3. And that's a constant, so it's infinitely significant. All right, so we're going to use that to find the energy in reactions, as well as energies in individual atoms. All right, so let's start with the first one. How much energy is lost in the reaction of cobalt-60 when it releases a beta emission and transmutates into nickel-60? Now, if there is 1 mole product and the reactants of product and reactants, and cobalt, the mass of cobalt is 59.93382 AMUs, and nickel is 59.93088 AMUs. Now, over here on the right, I have the atomic masses of the masses at atomic level of a proton, neutron, and electron. And since we're doing an electron, we're only going to have to look at the electron there. So we take the mass from the problem of the nickel and the mass of an electron, and last field called 1, 2, 3, 4, 5. So we're going to end up with 59.93143 U's. Now, we're going to subtract from that the mass of the reactant, and when we do that, we're going to get a negative value. And that makes sense because we're losing that much mass into energies being converted. So we're going to just convert that into grams because it says it's a mole. So therefore, we're going to take Einstein's equation, take 0.002398 grams, and then multiply that by 1 kilogram over 1,000 grams because we need it in kilograms. And then we multiply that by 3 times 10 to the 8th meters per second, and we're going to square that. Now, we take our units, a kilogram, meter squared per second squared, that is a joule. So take a calculator, 0.00239 grams times 3e8 squared equal, divide by 1,000 equal, and we get 2.15 times 10 to the 11th joules. That is a massive amount of energy. And that's one of the reasons why we use the atomic theory using of energy, because it produces so much energy in the individual reaction. All right, and that's per mole, and that's our answer. Now we can also work this backwards. Calculate the mass lost of 1 mole of a substance in a reaction. Carbon 11 to boron 11, where an electron is lost, if the reaction results in a release of 2.87 times 10 to the 11th joules. So how are we going to do this? We take Einstein's equation again, but this time we know the energy, and we know the speed of light squared, so we're going to divide those, and again, a kilogram meter squared per second squared divided by meter squared per second squared, made 2.87 times 10 to the 11th, divide by 3 times 10 to the 8th squared. We're going to generate, when my units cross out, 0.0000319 kilograms. That's awful big, so let's convert that into grams, 3 places to the right. We know with 0.00319 grams. So almost no mass or negligible amount of mass is actually lost in the reaction. All right, it reminds me when we had an nuclear engineer come talk to us in this class group I had, and he explained that every system on a nuclear attack sub is run by a vial about that long of uranium-238. So very little amount of mass produces a whole lot of energy. Nuclear energy is an abundant energy source and extremely efficient. All right, now the other thing that we can do is what's called energy from the binding energy. We talked about before, binding energy will hold the atom together. It's referred to as the weak force. Okay, so it's the energy that holds the nucleus together. It's the mass of an atom as compared to the mass of all the protons and neutrons. In the way that we find it is we take the mass of the protons and neutrons compared to the atomic mass, and that difference is what we call the mass defect. All right, so that being said, that being done, Let's look at a problem. Find the mass defect, the amount of energy that converts, amount of mass that converts to hold the atom together for helium per nucleus and per mole. All right, so what we're going to do, here's our protons, neutrons, electrons. Last time we just did electrons, but we're going to look at protons and neutrons today. So helium is 4/2. That means we have 2 protons and 2 neutrons. 2 times 1.0072776467 U's. And 2 times 1.00866491 U's. We multiply those through, those numbers we have, we add them up, we get that. Now from the periodic chart, which is right over here, we see that the atomic mass is 4.002602 U. That's a little more thorough number. When we fill last row column, we're going to get a difference of 0.029281. So that's the mass that's converted to energy to hold the atom together. All right, so we need this in grams to find the mass defect. So we're going to take our value and use Avogadro's number. So 1 gram of it is 6.02 times 10 to the 23rd U's. All right, now we got to convert to kilograms. 1 kilogram is 3 times 10 to the 8th. And then using the speed of light squared.
It's 1,000. It's 1,000 grams. Sorry about that. And then multiply by 3 times 8 squared.
Equation. When you take all those values, multiply them together, and divide through, we're going to get 4.3776 times 10 to the minus 12 joules per nucleus. Now that's a very small number. Remember, that's per each individual nucleus. It means per nucleus. How do we find it per mole? We're going to use Avogadro's number again. We take 6.02 times 10 to the 23rd nucleons, and that's a mole because 6.02 times 10 to the 23rd of anything is a mole. When we multiply those through, we get 2.653 times 10 to the 12th, a much more massive energy per mole, and those are our answers. Let's do one more of these, okay? Find mass for the binding energy of nitrogen. Now, if you want to pause this and work through this, we're going to show the steps for it. ltswpd@gmail.com. Like, subscribe, share. Any questions, let me know. Here we go. So we have our protons and neutrons for nitrogen. There's 7 and 7. We multiply those through, add them up, subtract them from the atomic mass, and we get that much of a mass loss and atomic level and mass defect. We're going to convert that using Avogadro's number to grams, and then convert to kilograms, multiply by the speed of light squared, and we're going to get 1.57 times 10 minus 11 joules per nucleon, and then to convert that, we're going to use Avogadro's number again per nucleons per 1 mole. Multiply through that, and we get 9.45 times 10 to the 12th joules per mole. Those are answers. Try here these, work through these. I'm just going to give the answers. Any questions, let me know. Comments, I'll try to respond back. All right, here we go. Ready? Those are our answers. All right, not too bad, hopefully. Take care. God bless.